So we're going to be talking about a species called the flying bison and their horn sizes. This is what a longhorn flying bison looks like. So there's a lot of information on this board, so let's just go ahead and start breaking it down. We have big A alleles, which will give you big horns. Big A alleles, which will give you small horns. And then little a, which will give you no horns. So let's take a look at this population right here. We have 1,000 total individual bison. We have 100 big horns, 600 small horns, and 300 hornless. So if we take a look at these two formulas right here, these will explain how we got the P and Q values. P being the frequency of just the big A, or just this by itself. Q being the frequency of just the little a by itself. So we take the frequency of the homozygous individual plus half the frequency of the heterozygous individual. And that's how we got 0.4 and 0.6. So if we move over here, we have a pretty big table with a lot of information on it. So let's start breaking that down. So we're going to assume that this population, our original population, is in Hardy-Weinberg equilibrium, which basically means it just meets the following assumptions. It's an infinitely large population, random mating, no selection, meaning all the genotypes are equally likely to survive, no migration in or out of the population, and no mutations. So we're just going to assume all those things are true for the sake of this problem. So we have the initial frequency, which we just use this equation to solve for the initial frequency. So we already have our P value, and then the frequency of big A is just P squared. And then big A is 2PQ. And then little a is Q squared. And then we have their fitness values, which basically is just how likely are they to survive in the wild. And then we have our unadjusted survivors, which once we add them all up, we get our average fitness. And we get the unadjusted survivors by multiplying the initial fitness, or the initial frequency times the fitness. So we just multiply these two to get this. Then add them all up, and we get our average frequency, or average fitness. And then the frequency after selection is just unadjusted survivors, so this divided by average fitness, which is this. So we just divide this by this to get this value. So let's talk about some selection that likely occurred here. As you can see, big A has the biggest fitness, big A has the next smallest, and then little a has the smallest. So since the values get lower as we go down, this means it's directional selection, which could likely be due to the fact that maybe the bighorn individuals are more likely to mate, or maybe they're more likely to capture prey, something like that. So that's why their fitness is much higher.